I am Dr. Sarala, Associate Professor of Mathematics, A.D.M. College, Nagapattinam. I am going to take now Measure Theory Unit 2, Integration of Functions of the Real Variable. Module 1, Integration of Non-Negative Functions. First of all, we have to see the simple function. A non-negative finite valued function phi of x taking only a finite number of different values is called a simple function. Just we have to take the finite values, but it is different values. So if a1, a2 and so on an are the distinct values taken by phi, any function phi, and ai which is equal to x is that phi of x which is equal to ai, a suffix I there, then phi of x which is equal to ai psi of a of x as ai which is equal to 1 to n. So here for every ai is measurable, then phi is also measurable. It is one of the notification. The next one, integral of phi. Let us take phi is a measurable simple function, then phi into dx which is equal to a suffix I m of ai as I which is equal to 1 to n, where ai which is equal to 1 to is a set, and then I which is equal to 1 to n is called the integral of phi. Next, integral of f. It is one of the definition. For any non-negative measurable function f, the integral of f dx is given by f dx which is equal to supremum of phi into dx, where the supremum is taken over all measurable simple function phi wherever phi is less than or equal to f. Both phi and f are functions. The next is integral of f over e. For any measurable set e and any non-negative measurable function f, then integration of f into dx which is equal to integration of f into psi suffix of e into dx. For now you will be using the above definitions. We have to derive one of the theorem. The statement it becomes, if phi is a measurable simple function, then prove that first one step, that is integration of phi into dx which is equal to summation over n a into m of m is nothing but measure m of ai integration of e for any measurable set e. The second one, integration of a union b of x into dx which is equal to integration of a of phi into dx plus b into phi into dx for any disjoint measurable sets a and b. The third one, integration of a into phi dx which is equal to a into integration of phi dx if a is greater than 0. The proof is nothing but first one we will take the integration of phi definition, that is integration of phi into dx which is equal to summation over n ai into m of ai, where I which is equal to 1 to n, that is equation 1. Any and then we will take integrals of f over e definition, that is integration of e f into dx which is equal to integration of f into psi e into dx, that is equation 2. So now we will take these two definitions, we get the result integration of phi into dx which is equal to summation of over n ai into m of ai intersection. The next one, second definition, the right hand side we will take, that is integration of a of x into dx plus b integration of b of phi into dx which is equal to summation over ai m of a intersection ai plus ai m of b intersection ai by equation 1. The next one, that is a definition for integration of phi. The next one, integration over n ai into m of, we will combine these two equations, we will get the result m of a union b intersection ai. The result it becomes integration of a union b of x into dx. This is nothing but the left hand side. So right hand side equal to left hand side, that is integration of a of phi into dx plus b of integration of b of x into phi into dx equal to integration of a union b of phi into dx. The next second one definition statement it becomes, in the proof it becomes, since integration of phi into dx which is equal to summation over n ai into m of a, that is equal to, using the definition, integration of a phi into dx which is equal to summation over n a into ai of m of ai. That is nothing but a into summation over a m of ai. That is equal to a into integration of phi into dx. All these are given by above the definition. That is equal to right hand side if a is greater than 0. The next theorem, so the proof it, the two results are proved. The next theorem 2, let f and g be non-negative measurable functions. Then prove that first one, if f less than or equal to g, then integration of f dx is less than or equal to integration of g dx. The second one, if a is a measurable set and f is less than or equal to g on a, then integration of af dx is less than or equal to integration of ag into dx. The third one, if a is greater than or equal to 0, then integration of af into dx equal to a into integration of f dx. The fourth one, if a and b are measurable sets and a is the superset of b, then integration of af into dx is greater than or equal to integration of bf into dx. The proof, since the integral of f definition, it becomes integration of f into dx equal to supremum of integration of phi dx wherever phi is less than or equal to f. If f is less than or equal to g, then integration of g dx equal to supremum of integration of f into dx is greater than or equal to integration of f into dx. So from the definition of integral, the given equation, it becomes integration of f dx equal to integration of g dx. So if a is the measurable set and f is less than or equal to g on a, then by first result and the definition over the integral of integration of f over e, that is integration of e f into dx equal to integration of f into psi e of dx, we get the result that becomes integration of a into f dx is less than or equal to integration of a into g dx. So if a equal to 0, the given result is true. Suppose a is greater than 0, phi is measurable simple function with phi which is less than or equal to af, if and only if phi which is equal to a psi, where psi is a simple psi is less than or equal to f, and then integration of f dx equal to integration of a psi into dx, wherever phi which is equal to a psi. So that integration of phi dx which is equal to a into integration of psi dx. So integration of af into dx which is equal to the integral f function given by supremum of integration of phi into dx. That is nothing but supremum of integration of a psi into dx. That is equal to a into supremum of integration of psi into dx. So integration of af into dx equal to a into integration of f dx. So if a and b are measurable sets and a is superset of b, it follows that psi a of f is greater than or equal to psi b of f for whenever a is greater than or equal to b. The next, by equation 1, integration over b f into dx is less than or equal to integration over a f into dx. So it is nothing but integration of a into f into dx is greater than or equal to integration over b f into dx. So the next theorem is theorem 3, Fato's lemma. It is very important one. Let fn n equal to 1, 2, 3 and so on be a sequences of non-negative measurable functions. Then prove that limit infimum of integration of f into dx is greater than or equal to integration of limit of infimum of fn into dx. It is a great result one. The proof it becomes, let us take fn function. It is given in a statement n equal to 1 to infinity be a sequences of non-negative measurable functions. Let us take now f which is equal to limit infimum of fn. That is equation 1. So, for each measurable simple function phi, with if phi is less than or equal to f, we have integration of phi into dx is less than or equal to limit infimum of integration of fn into dx, that is equation 2. So, by the definition, integration of f into dx equal to supremum of integration of phi into dx. So, here this theorem having two cases. First one case is integration of phi into dx equal to infinity. So, by the integral of phi, integration of phi into dx equal to summation over n I ai of m into ai. So, for some measurable set a, we have m of a which is equal to infinity. So, phi, whenever phi is greater than a greater than 0 on the measurable set a, that is equation 3. So, from this we will say that an is an subset of an plus 1 for each n. From this we will say that it is a monotonically increasing sequence. So, let us take, we will define one of the measurable function, that is gk of x, which is equal to infimum over j greater than or equal to k fj of x, and the measurable set an which is equal to x is that gk of x which is greater than a for all k is greater than or equal to n, which is a measurable set. For each psi I, gk of x is a monotonically increasing sequence, and limit k tends to infinity, gk of x which is equal to f of x which is greater than or equal to phi of x. So, a is the superset of union over n to 1 n equal to 1 to infinity an. Hence, limit m of an which is equal to infinity, because the given statement it becomes phi of x which is equal to infinity. So, the limit m of an which is equal to infinity using that result. But for each n, integration of f1 dx is greater than or equal to integration of gn into dx which is greater than a into m of an. So, limit infimum of integration of f1 into dx equal to infinity by using the above third result and the second result. So, the result is holds. The next second case, that is integration of phi into dx is less than infinity. So, remember that the first case it is equal to infinity, the second case this is less than infinity. So, for this we will define again the measurable set b which is equal to x is that phi of x which is greater than 0, and then m of b which is less than infinity. So, define m be a largest value of phi, and if 0 less than epsilon less than 1, let us take bn is the measurable set, that is equal to x is that gk of x which is greater than 1 minus c phi of x k is greater than or equal to n. So, wherever gk of x equal to infimum over j greater than or equal to k fj of x, then the set bn is a measurable set. So, bn is a subset of bn plus 1 for each n, and then b which is the subset of union over n equal to 1 to infinity bn. So, b minus bn is a decreasing sequence of the set b, then b minus bn which is equal to mt. So, m of b which is less than infinity, there exists a set n such that m of b minus bn is less than epsilon for all n greater than or equal to capital N. If n is greater than or equal to capital N, integration of gn into dx which is greater than or equal to integration of b into gn dx, which is greater than 1 minus epsilon into b of pi x into dx. So which is greater than or equal to, you will be using the above steps, 1 minus epsilon into integration of b into phi into dx minus integration of b minus bn into phi into dx. Again, which is greater than or equal to 1 minus epsilon into integration of phi into dx minus integration of b minus bn of phi into dx. Again, greater than or equal to integration of phi dx minus epsilon into integration of phi dx minus epsilon into m. Since epsilon is an arbitrary set, then fn is greater than or equal to gn. Limit infimum of integration of gn dx is greater than or equal to integration of phi into dx. Hence the proof. So the next one, theorem 4, Lebesgue monotone convergence sequence. Let us take fn such that n equal to 1, 2, 3 and so on infinity be a sequences of non-negative measurable functions such that fn of x is monotonically increasing sequence for each x. Let f equal to limit fn, then prove that integration of f into dx equal to limit integration of fn into dx. For proving this result, we have to take the Fato's lemma result. So Fato's lemma gives the result, it becomes integration of f into dx equal to integration of limit infimum of fn into dx, which is less than or equal to limit infimum of integration of fn into dx. This line is taken as becomes first equation. The next, but f is greater than or equal to fn by using the hypothesis. So integration of f into dx is greater than or equal to integration of fn into dx. Hence, integration of f into dx is greater than or equal to limit supremum of integration of fn into dx. That is equation 2. So you will be combining these two results. So first result, integration of f into dx is less than or equal to limit infimum of integration of fn into dx. The second result is integration of f into dx is greater than or equal to limit supremum of integration of fn into dx. Combining these two equations, we get the result, integration of fn into dx equal to limit infimum of fn into dx. So the next one, theorem 5, let f be a non-negative measurable function, then there exists a sequence phi n of measurable simple functions such that for each x, phi n of x is monotonically increasing to f of x. Proof is, by the construction proof, given f be a non-negative measurable function. Let us take the measurable set that becomes E, which is equal to, for this we will construct the measurable set E equal to x is that k minus 1 by 2 power n, which is less than f of x, which is less than k by 2 power n, where k equal to 1, 2, 3 and so on n into 2 power n, and f which is equal to x is that f of x greater than n. So let us put phi into nk, which is equal to summation over k minus 1 by 2 power n psi of E n k plus n psi of fn. Then the function phi n are measurable simple functions, and phi of n plus 1 of x, which is greater than or equal to phi n of x for each x. If f of x is finite and x which is belongs to complement of fn for all n, then f of x minus phi n of x, which is less than or equal to 2 power n. Therefore, phi n of x is monotonically increasing to f of x. If f of x equal to infinity, then it belongs to b power n fn. Therefore, phi n of x, which is equal to n for all n, and fn of x is monotonically increasing to f of x. That is the proof. The next, theorem 6, let f and g be a non-negative measurable functions, then prove that integration of f into dx plus integration of g into dx equal to integration of f plus g into dx. Just we will take the simple functions of phi and psi for this proof. So let us take the values of phi be a1, a2 and so on an. taken on the sets A1, A2, capital A1, capital A2 and so on An. And also the values of psi b, b1, b2 and so on bm taken on the set b1, b2 and so on bm. Then the simple function phi plus psi has the values ai plus bj on the measurable sets ai intersection bj. We get the result integration of an intersection b of phi plus psi into dx equal to integration of a intersection b of phi into dx plus integration of a intersection b of psi into dx. That is equation 1. The next, by the union we will take nm disjoint sets ai intersection bj in capital R, that is the real value variables. Then the equation 2 becomes some integration of phi plus psi into dx equal to integration of phi dx plus integration of psi into dx, that is equation 2. So let us take f and g be any non-negative measurable functions. Let phi n plus psi n, phi n comma psi n be the sequence of measurable simple functions. Then phi n monotonically increasing to f and psi m monotonically increasing to g. Then phi n plus psi n monotonically increasing to f plus g, that is third equation. Using this equation is getting from the equation 1 and 2. So by 2 integration of phi n into psi n dx equal to integration of phi n dx plus integration of psi n dx. So taking the limits on both sides, we get the result integration of f plus g into dx, which is equal to integration of f dx plus integration of g dx. That is the result. The next one, theorem 7. Let f1 be a sequence of non-negative measurable functions, then integration of summation of f1 into dx, which is equal to summation of integration of f1 into dx. So already know that one of the result that becomes, let us take f and g be a non-negative measurable functions, then integration of f plus g into dx equal to integration of f dx plus integration of g dx. That is equation 1. This is previous result. By induction result 1 implies the sum of n functions. Let us take if an which is equal to summation of fi, then integration of s and dx equal to integration over n summation of integration of fi into dx, that is equation 2. So but phi n is monotonically increasing to f, this result is already true. So which is equal to summation over n fi. So using monotonically in convergence sequence theorem, equation 2 becomes integration of summation over n f infinity into fn into dx, which is equal to summation over n integration of fn into dx. That is the result, final result. Thank you.